This is lecture 2. Of our linear algebra course. So what we are going to do today is we are going to learn how to solve the system of equation using algebraic methods. But let's first recall the things that we had done in the previous class. So we talked about something called the system of equations. So whenever I say equations, I mean linear equations. Then we talked about the number of solutions of such a system of equations. And the third thing we talked about is, given the system of equations, the so-called the row picture and the column picture. Okay. Now, we will build upon these things and we'll see how these things help us solve a system of equations. Now, before we do that, I'd like to introduce two terms. One of them is the consistent system. What it means is systems having at least one solution. And the other category is the inconsistent systems. And this means systems having no solutions. So given a system of equations, we will always be able to categorize in these two things. And when we say consistent system, it covers both the cases when the system has exactly one solution and when the system has more than one solution, that is infinitely many solutions. Okay. Now, given the system of equations, we had talked about the augmented matrix. So let us see, if I take up an example of x plus 3y is equal to 4 and 5x minus 4y is equal to minus 7. So given this system of equations, we had talked about an augmented matrix. This is the augmented matrix we have referred to. Oops. This is what we call as the coefficient matrix, and this was our right-hand side vector B. Okay. What we want to do is, given the system of equation, we want to reduce it to a nicer form. And what I mean by a nice form is, we'll be clear in a moment. We want to reduce it to a nice form, say something like this. 1, 0, 0, 1. Something comes up here, something comes up here. We shall see the advantage of reducing it to that nice form, that once we have this form, we will be able to read out the solutions fairly quickly, and hence we would know whether the system is consistent or it is inconsistent. Now the question is it always possible for us to achieve this form? That means whatever we are doing, the so-called reduction, is it always possible to start with a matrix and reduce it to this nice form? We shall answer that question once we learn how to do this reduction. So we want to talk about what exactly it does mean to reduce a matrix. What are the kind of operations involved? So in order to reduce a matrix, we will use a bunch of things we call as the row operations. The technical term for it is elementary row operations, but we don't need to emphasize on elementary for now, but later on we shall see why we call them as elementary row operations. So the things that we do under row operations are we swap rows. We multiply one row by a non-zero scalar. And there's another row operation that we can perform, which is perhaps the most widely used row operation, is basically adding a multiple of one row to another row. Now, one may question, why are we performing these row operations? What do we think we will be able to achieve out of these row operations? And why have we only selected these three operations to achieve that kind of a nice form of a matrix? To better understand this, that why we have confined ourselves to these operations, or what are they really helping us achieve, let us go back to the system that we have started the whole thing, the system of equations that we were dealing with. Now remember, if I'm given this system of equations, I'm interested in finding its solutions. So what we are claiming is, if we perform any of these operations on this system of equation, it will not change the solution. So for example, if I swap rows, what if I treat this as my first equation, that as my second equation? Will it make any difference? And it's kind of intuitive, very obvious that swapping the order of the equations will not really have any effect on the solution. What about the second row operation? It says multiply one row by a non-zero scalar. What it means is, what if I take one of these equations, whichever one we like, and multiply it by a non-zero scalar? Say for example, if I multiply the first equation by a 2, so I get 2x plus 6y is equal to 8, and 5x minus 4y is equal to minus 7. Once I have multiplied it by 2, I have got a new system of equation where at least the first equation looks a bit different from the first equation in the system. Can I not say that whatever is the solution to this system will still be the solution to this system and vice versa? So that means performing this kind of a multiplication of one particular equation by a non-zero scalar will not change the solution whatsoever. What about the third operation? Third operation is the one which is the least obvious. Why is it not affecting, or why is it not changing the solutions to the system of equation? So let's see. If I'm given this, let me call this as equation 1, and let me call this as equation 2. What if I took equation 1, multiplied it by some scalar, let us say minus 5, and added it to equation 2. So as you can see, we are performing the kind of row operation suggested here, adding a multiple of one row to another row. So that means adding a multiple of one equation to another equation. So what do we get? X plus 3y is equal to 4 remains as is. And I'm using that equation to do something to the second equation. If we do that, what we are going to get is minus 19y is equal to minus 27. So I have achieved a new system of equation from the old one. So the question we are asking is, will the solution set of the new system be the same as the solution set of the old system? Because if it does, then that means this row operation will also help us preserve solution. Hence, we can keep on doing this until we find the right form. So, of course, there's an algebraic way to understand this, but let me share with you the geometric way of doing this. So, imagine we are trying to plot these lines. So let's look at this line, x plus 3y is equal to 4. Perhaps it is something like this, x plus 3y is equal to 4. And let me give this line a name, L1. Okay. Then we have another line, 5x minus 4y is equal to minus 7. And if we draw this line, maybe this line looks something like this. Okay. If it looks something like this, say 5x minus 4y is equal to minus 7. Let me call this as the line L2. Now, let us ask ourselves, how did we get this new line, which we are calling as 19y minus 19y is equal to minus 27. If I plot this line turns out to be a horizontal line which exactly passes through this point. Okay. This I claim is the line minus 19y is minus 27. And let me give this guy the name L3. Now one may say, well, how am I so sure that my line will pass through this point unless I already knew the solution? But the reason I plotted this way is, I'll show you in a moment why this must be true. Let us try to think slightly differently. Imagine your line L3. Okay. The way we have obtained line L3 is using line L1 and line L2. So what we did was we did set minus 5 times line L1 plus line L2 has produced us the line L3. Now what if we try to write this in a different format? Can we say minus 5 times L1? So for L1, let us consider the expression x plus 3y minus 4. If you look at this expression, this is the expression which will help us represent the line L1. And whenever this expression is 0, that means we are on line L1. Likewise, if we talk about this expression 5x minus 4y plus 7. If you look at this expression, whenever this is 0, it will represent line L2. And whenever it is not 0, it is not representing the points on line L2. But if you combine these guys, can we say that we are going to get minus 19y plus 27. Now if you look at the final expression we have got, this expression would be 0 only when the point lies on this horizontal line. Now, can we say, if we mark this point as P, can we say when we plug in the coordinates for P in here, then this will give me a 0. Likewise, if I plug in the coordinates of P in there, this will also give me a 0, because the point P lies on both lines L1 and L2, which means those two expressions are 0 at P. So can we say that at P, the value of that expression will also turn out to be 0, hence the point P lies on line L3. So that way, at least by this example, we can convince ourselves that as long as we are taking linear combinations of two lines and producing a third line out of it, that third line will always pass through the intersection of the first two lines we started with. So that kind of gives us a heuristic idea that why that third row operation would also preserve the solution. It's just that instead of these two lines, now we are working with these two lines and getting the answer, maybe in an easier manner. Okay. So let's see how are we going to now achieve this form. By the way, this form has a name, so let's first understand the terminology, and then we'll worry about solving the system of equations. Okay, so let's talk about the two terms associated with matrix. One of them we will call as the echelon form. So now we want to refer to the echelon form of a matrix. Now, when we say echelon form of a matrix, what exactly we mean? So suppose I have a matrix M. So M is in echelon form. If the following conditions are met, all the 0 rows are at the bottom. And the leading non-zero entry of each row is to the right of the leading non-zero entry of the row above it. So if a matrix satisfies these these conditions, then we will say that matrix is in the echelon form. Otherwise, it is not in the echelon form. Okay. So let's try to see some examples and see if we can identify, we can understand what is an echelon form or what is not. So for example, let's take a look at this matrix. Is this in echelon form or is it not? Let's see. All the 0 rows must be at the bottom. Well, this is a 0 row, it is at the bottom. The leading non-zero entry. Now, what exactly do I mean by leading non-zero entry? Well, leading non-zero entry would simply mean the very first entry in each row, which is non-zero. So for example, in here, this is the leading non-zero entry. 1 is the leading non-zero entry in the first row. So each leading non-zero entry of each row should be to the right of the leading non-zero entry of the row above it. Well, there's no row above it, so this condition will be met without any problems. So this we will say is in echelon form. Now, how about another example and see whether this is in echelon form or not. Let's try this example, 1, 2, 3, 0, 1, 0, 0, 1, 0. Is this in echelon form? Well, there are no 0 rows, so we don't have to worry about them. The leading non-zero entry. So this is the leading non-zero entry in first row, this is the leading non-zero entry in the second row, and this is the leading non-zero entry in the third row. As we can see, the leading non-zero entry out here is to the right of the leading non-zero entry above it. So this is okay as far as echelon is concerned. But out here, the leading non-zero entry is right below the leading non-zero entry of the row above it. So this is not fulfilling the criteria, so this is not in the echelon form. Let's try to see another example and see if that is an echelon form or not. So let's try and see something like this. Is this in echelon form or not? So let's see the leading non-zero entries. There are no zero rows, so we only worry about the leading non-zero entries. And these are the leading non-zero entries of their respective rows. And each leading non-zero entry is occurring to the right of the leading non-zero entry above it. So it's kind of staggered in such a manner, it's like a staircase pattern. So this thing is indeed in the echelon form. Now, while we are at it, we might as well introduce another term, which is closely related to echelon form. Initially, we may not really understand the significance why we are going after it, but soon we will see. And this term has its own merit: row-reduced echelon form. So I will generally refer it to as the RREF. It's not a standard terminology, but it will at least help me not write this long phrase, row-reduced echelon form. So what it sees and what it includes is, we will say the matrix M is in the row-reduced echelon form if M is in echelon form. At least that takes care of the echelon part of this phrase. The second thing is, why are we saying it is row reduced? Well, all the leading non-zero entries must be 1. And there's another criteria that we want, that all the other entries in the column with leading 1 should be 0. So if a matrix satisfies all these three things, then we will say it is in its row-reduced echelon form. So let's try and see what happens. This is an echelon. Is it row-reduced echelon form? Well, all the leading non-zero entries must be 1. So our leading non-zero entry is 1. All the other entries in the column with leading 1 should be 0. All the entries in the column with leading 1 is 0. So this is indeed in the row-reduced echelon form. Let's talk about this one. Well, if it is not echelon, it can't be row-reduced echelon form. What about this one? All the leading non-zero entries must be 1. Well, out here, this is the leading non-zero entry, which is not 1. Hence, it is not in the row-reduced echelon form. So the question is, why are we so fond of the echelon form, or the row-reduced echelon form? And how are they going to help us? From theoretical perspective, echelon form and row-reduced echelon form are not that much different, in the sense, whatever I can get out of echelon form or a whatever I can get out of row-reduced echelon form, pretty much I can find those things from echelon form also. However, from a computational perspective, it's a balancing act. To get the row-reduced echelon form, you have to do extra computation, but in the end, you can read out solutions much more effectively, and there's no requirement of back substitution. However, out here, you may have to do less computations to get the echelon form, but then you have to do back substitution to get those solutions. So from computation point of view, there might be some difference between the two, but we will see what are the differences for us as far as knowing the property of the matrix is concerned based on these things. So in a nutshell, what we want to do is, given an augmented matrix, we want to see how to get its echelon form and how to get its row-reduced echelon form. So let me start with the same example that we were trying to solve. And this time we try to get its row-reduced echelon form. So the numbers I had used were 1, 3, 4, 5, minus 4, minus 7. And our objective is to get its row reduced echelon form. We want to do some row operations and end up getting the row reduced echelon forms. Now, one thing I should point it out, that even though this is an augmented matrix, but it has like the row operations will work exactly the same way as if they would work on any matrix. So let's try and see what are we going to achieve. Remember, we want the row reduced echelon form, so we can perform some row operations as follows. So what I can do is, I see that I have a leading 1. So anything below it or above it, well, there's no above it, so everything below it should become 0. So in order to achieve that, I can perform this row operation, adding a multiple of the first row to the second row. So what I did was add the appropriate multiple so that I can use this entry to eliminate the entry below it. And once I do that, remember I'm using the first row as a tool or as a multiplier, so that thing remains unchanged. And I'm going to get the change in the second row.